All right. Hi guys, how's everyone doing? So first of all, let me welcome you all to Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And on this JEE English channel, every concept is being taught to you completely in English so that none of you students feel left behind. All right, so today is the lecture 2 of this series, which is meant for class 11 students. So here we are taking up class 11 topics one by one, and we're discussing the very basics from the very scratch. All right. So this is lecture 2 of Newton's laws, and today we'll be talking about forces and the laws of motion. All right. So before we start, let me introduce myself one more time. Hi Amy, how are you? Hello Arpit. Good evening to you as well. So for those of you who don't know me, my name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for the past almost 8 years, I've been teaching physics for IIT JEE. And all this teaching has been in the offline setup, and I have been a part of some of the most premium institutes in India for the JEE prep. All right, I myself was JEE rank 447, and I've already coached many students to top ranks in the offline setup. I hope to keep continue doing that in the online setup with this opportunity provided to me as well as the students with the help of Unacademy Plus. So why don't we talk about the Unacademy subscription first before moving ahead? So your Unacademy subscriptions come with benefits like live classes. You get to interact with your educators on a regular basis. All right. So trust me, these benefits make your classrooms very interactive, and the experience is very close to your offline coachings. So the learning is very effective because of all these features. Then you have live polls and leaderboards, which make your classrooms highly interactive. You also have test series and analysis, and then you have live doubt clearing sessions, which is very important because I know students are most bothered about their doubts. You know, even at this time, I keep getting messages from students all the time. I get so many messages daily that I can't tell you, and all of them are about solving their doubts. All right, so yes, at this hour, when all of us are at home, we can't step out, so that becomes a huge problem. Now that will be taken care of with your Unacademy courses, because as a compulsory feature, all Unacademy Plus courses feature a live doubt clearing session after every 3 sessions. All right, so don't worry, with this subscription you will never have any doubts left. All right. So moving forward, not only does the Unacademy subscription give you these benefits, it's also giving you access to India's top educators. All right. So what Unacademy has done, it is bringing all the top educators from all across India on a single platform. So I think that's a great opportunity for all you guys sitting at the comforts of your home. Now you have access to such a quality educator pool. All right. So how do you get your Unacademy subscriptions? It's very simple. First, you install the app. Once you've installed the app, you go to the plus section, you select your goal as IIT JEE and click on that get subscription button. Now, when you're getting your subscriptions, you will realize that the fees of subscriptions is very small. I mean, the 12-month subscription comes to about 2,500 a month, and the 24-month subscription is coming to about 1,500 a month, which is highly beneficial. All right, trust me, people, I know the kind of fees people pay in their offline coaching setups, and this is not even comparable to what people pay for their home tuitions. All right, so at these prices, I think with all the benefits that Unacademy Plus has to offer, this subscription is a must-have. So remember, when you're getting your subscriptions, you can use my code, which is RD Live, to get your subscriptions. So this code will not only unlock all the wonderful features of the Unacademy Plus, it will also give you an additional 10% off on your subscription fee, which will make this already very attractive and affordable pricing even more attractive. All right. So remember to use this code and get an additional 10% off. So you realize this cost of 1,500 per month would be reduced to 1,350 per month. I mean, at that price, I think it's just a must-have. All right. Next, for those of you who are following us on the JEE English channel, you can connect with us on the Telegram app using the link shown above, so that you're not missing out on any notifications regarding any lectures or sessions being conducted on the JEE English channel. Now, without any delay, let's. Are you coming on Plus from 2nd September? Not today evening. Please teach more problems on calorimetry. Okay. Okay. See, Sabresh, my aim is hi Pavan. How is everyone? Yes. I know. Rahul sir is starting course courses from 2nd of September, but I most probably will be starting around 15th of September. All right. So most likely from 15th of September, I'll be starting my courses. Actually, the thing is, I conduct 2 classes daily on YouTube, so my schedule is slightly more busy. All right. But yeah, we do plan to start launching these courses in September itself. So don't worry. I think maximum by 15th of September. I think Math sir, Abhinav sir, and I both would be launching our courses on the Plus. All right. Okay. So again, as I said, Sabrish, as far as your problems of calorimetry is concerned, okay, I'll maybe include a couple more, but most of the practice regarding calorimetry you should be doing on your own. See, my class for that session is mainly meant for revision. Yes, I know. So I will maybe discuss a few more problems, but again, it's meant for quick revision of concepts. So the practice part you should be doing at home. All right. Chandrasekhar, batches. Okay, so batches, I'm not still sure. We are discussing that. I am in talks with the Unacademy team. We will see. Actually, they what they had to say was that we will only launch batches if there are enough students which we find to be interested in opting for those batches. So I don't know. I think maybe you can get in touch with the Unacademy team to fill the form below and request for batches on Plus. All right. So if more and more students are asking for batches, then most likely they will start the batches. Okay. All right. So why don't we get started with today's discussion? So yes, last lecture we were discussing about forces. We discussed about normal reaction. We discussed tension. And today we'll start our discussion with the discussion of spring force. All right. Dargo says, sir, any topics to concentrate more about advance? Okay, so advance, actually, you see, advance usually asks you problems where you have mixed concepts. All right, so in one problem, they would ask you concepts of momentum, work power, energy, and let's say rotation also. So most of the problems in advance are designed like that. So it won't be wise to leave out on any topic as such. But yeah, as far as the most important parts are concerned, I think definitely electromagnetism and mechanics constitute the most important part. And of late, I think advance has been focusing a lot on modern physics also. So I would definitely recommend that you should definitely take care of mechanics, electromagnetism, and modern. That is a must. Okay. Okay. All right. So why don't we get back to the discussion for the day? So spring force. So what is a spring force? So when a spring is either compressed or elongated from its natural length, it exerts a force opposite to the direction of deformation. All right. So you guys should know that this is what a spring looks like. All right. And now when left alone, the spring has a length which is called its natural length. So if you're not touching the spring, it takes a length which is called its natural length. Okay. Now, the spring has a property that it has the tendency of always trying to maintain its natural length. So if you push it from its natural length, if you shorten the length, then it tries to come back again to the natural length. Then if you elongate it, then also it tries to come back. So for that, what it has to do, if I start pushing a spring, it has to push back because it wants to come back to its natural length. Similarly, if I pull the spring, it again pulls. Now this time it starts pulling because it again wants to come back to its natural length. So you have to remember that springs have a tendency of always trying to maintain their natural lengths, and they will oppose any change in their natural lengths. Now, obviously, the force of the spring, as I told you, that all forces in some way or the other are either gravitational or electromagnetic. Every force that you will encounter. So this force also turns out as electromagnetic in nature. Fundamentally, it's an electromagnetic force. All right. Next, again, since we realize that this force can be push and pull both. All right, and it always acts along the length of the string. So imagine this: if you have a spring, all right, like this, and if you applied a force like this, so this force would have two components, right? So one component would be like this, one component would be like this. Now you realize this component is not changing the length of the spring. Only this component changes the length of the spring. If I take a spring and if I just twist it like this, then the spring length does not change. All right, then it does not oppose such a movement. However, if you make a movement along the length of the spring, that is what it will oppose. Okay, so Noman is saying, sir, I want free subscription. Okay. Okay, I don't know how to get free subscriptions. I don't think Unacademy is giving free subscriptions. This subscription is almost free only in any case. It's 1500 rupee a month. What more do you want? What is that thing in spring? I mean, how does spring does this? Like a wire, it will not do this, but when wire is bent, it has the ability. This ability, is it a superpower? Okay, that's just how the springs are designed. That is just how the elastic properties of these materials are. Alright, we will talk about elasticity later. So you will realize that every material has certain elastic properties. Wherein every material actually has a tendency of, maintaining its original shape and size. Okay. Alright. Okay, okay. You realize, Dark Ghost, that maintaining the app software, that also costs money. Plus, we guys also get paid by Unacademy. So Unacademy has those expenses. Have you ever gone to a reputed offline coaching? Have you gone to a reputed offline coaching? Have you seen the kind of fees that they charge, Dark Ghost? Trust me, I was for the longest duration of my teaching career, I was a part of FitJEE. Do you have any idea how much is the fees there for a 2-year course? All right. What is my salary? Okay, decent enough. I'm not supposed to discuss all that. It's decent enough, of course. Of course. You realize I am from IIT. I could have worked anywhere and earned good amount of money. So even if I'm working here, I have to be earning that kind of money. So the kind of salaries I get are at par of what my all my other batchmates are getting. No, Arpit, you are wrong. Yes, it is more than FitJEE here. Okay. So anyhow, so I'll tell you an estimate. Dark Ghost, FitJEE fees would be around 10 times the fees that Unacademy is charging you. Okay. So Dark Ghost, so I hope you realize that. So if you go into an offline setup, trust me, they are charging you fees which are at least 10 times the fees that Unacademy is charging you. Okay, how it is electromagnetic? Yes, you are right, Sabresh. So let's just stick to the topic again. How is it electromagnetic? Okay, so let me tell you. As I said, yes. So obviously, Unacademy has to take care of its expenses also. They have to charge fees. Alright, in any case, this is very, very reasonable. In any case, I'm telling you, I've seen the kind of fees that people are paying elsewhere. Alright, anyhow, let's get back to the topic. No, Arpit, it is much more than that. It is much more than that. For 2 years, it is at least 3 times that. Yeah, I know. I know what you're saying. My salary is way more. Don't worry. But the fees that offline coachings charge, minimum would be 5 times what Unacademy is charging for 2 years, that is. Or rather 6 times. I think it ranges from 6 times what Unacademy is charging to at least 10 times. That is the range of offline coaching fees. Not even 10, maybe 12 times also. Alright, that is the kind of fees that offline coachings charge you. In Fiji, it was around 12 times the fees that Unacademy is charging. In most other less reputed institutes also, the fees would be at least 6 times what Unacademy is charging you. All right. Anyhow, coming back to the discussion. So somebody asked, how is this force electromagnetic in nature? So let me tell you. I told you guys that every material has a property that it wants to maintain its original shape and size. So let's see if I can take up some example. Okay, just hang on a minute. So for the sake of simplicity, let's just take this cable. All right, so if you have this cable, if I bend this, it comes back. All right, it comes back to its original position, right? So how is it doing that? How is it doing that? That is because of all the intermolecular attractions that are there. All right, this cable wants to stay like this. If I change its position, if I bend it, the moment I release it, it straightens up back. So the force responsible for making it come back to its straight position is the intermolecular forces that it has. Those are electromagnetic in nature. All right. So those are electromagnetic in nature. That is why I'm saying that this force also, spring force, is also electromagnetic in nature. So when you have a spring, when you are stretching it, the reason why it wants to come back is because of its structure. Because of its structure, it wants to, regain its shape and size. So Norman, as you asked, answer to Norman's problem. It's not only spring that has this property. Everything has this property. All right, as I just showed you. In this case, see, this is also coming back to its original shape. All right, it always straightens up. So that is the point. It's not only springs that have this property, but springs are designed in a way where this property is very prominent. Okay. I hope you got your answer, Norman. It is just the way it has been designed is that this property becomes very, very prominent, that it always wants to maintain its length. Okay. Now, as I said, if I applied such a force, then it will have two components, and only this component would be able to produce a change in length. All right. Similarly, if I had this kind of force, then the components would have been like this, like this. Only this component is producing a change in length. And whenever you produce a change in length, that is what the spring is trying to oppose. Okay. And that is why the spring force is always along the length of the spring. Okay. So as I said, this force is pull and push both and always acts along the length of the string. Remember this. Now this force has a magnitude which is Fx equals minus Kx. Alright. So experimentally, this is what Robert Hooke had given as Hooke's law. Alright. So he performed a lot of experiments with springs and he realized that the spring force varies as F of spring is minus times Kx. Alright. So if you draw a graph, of that, this is what the graph of spring force looks like. Alright, if on this hand you have a graph of F of spring and this is your x being the elongation or the deformation. Now whenever there is elongation we call that positive and deformations we call them negative. So this is a graph which goes like this. This is a straight line graph. Alright, so that is how you will see the graph as. Now you see that what is happening is that the force that it is trying to act in order to come back to the original position is directly proportional to the elongation. So if I stretch it by x and suppose the spring applies a force of 1 Newton, then if I stretch it by 2x, then it will apply a force of 2 Newton. Okay. The more the deformation, the stronger is the force that it tries to apply for getting reformed to its original shape. How is it electromagnetic? I already answered that, Arpit. Arpit, I've already answered how it is electromagnetic. Alright, so this equation is called Hooke's law. Hooke's law. Alright, so it was noticed that experimentally F of spring is directly proportional to x. Alright, so if you remove the proportionality constant, then you have Fs equals minus times Kx. The minus sign denotes that the direction of the force of spring is always opposite to that of x. Okay. If your x is positive, which means you are elongating the spring, then the force is in the negative x direction. If you are compressing the spring, which means x is in negative x direction, then the force would be in positive x direction. It will try to push back. Okay. and this is known as Hooke's law. All right, and this k is called the spring constant. So this k is called the spring constant. Okay, so spring constant is a property of the spring. It depends on the size, material, and even the shape, the kind of turnings that it has. So spring constant is a property of the spring, and this will only be determined experimentally. All right, you can design springs differently to change the case. All right, but once you have designed the spring, the way to measure the spring constant is experimentally. So you compress it by some x, you measure the force, and you will find the spring constant k. All right. Next, as I said, this force is also self-adjusting. As I said, it will adjust itself according to the x. However, it can't self-adjust instantaneously. This is a very, very important point. The force of spring cannot change itself instantaneously. Why? Because the force of spring is always like this. It is equal to minus kx. So if the force of spring changes instantaneously, what does that mean? That just means that your x changed instantaneously. Now x can never change instantaneously. To change the x instantaneously, what does that mean? That I pulled it from here to here within almost negligible time. All right, within no time, which means the speed of this end would have been close to infinity. All right, so since the length of the spring cannot change instantaneously, the spring force can never change instantaneously. So this is another very important point that you need to remember. Now, in this figure, you will notice that here, if the relaxed length is shown like this, what you realize is that this obviously practically cannot be compressed to any level. And practically, you know that you cannot stretch any spring to any level. All right, you can only compress it to a certain level where, you know, when all these will start touching each other, and beyond that, you won't be able to compress. Similarly, practically what happens is if you stretch a spring, you realize if you keep on stretching, this thing will start uncoiling. And then the spring becomes, it gets damaged. Okay, it no longer, starts behaving like a normal spring. So it will behave like a spring as long as the elongation is within a certain limit. However, if I keep on stretching a spring, eventually its coils will get destroyed. Okay, the coils would get damaged, and it will stop behaving like a normal spring. However, when we are studying Newton's laws, we will treat all springs as perfectly ideal. Now, what are the properties of perfectly ideal springs? So, ideal springs, one, are massless. Second, they have no friction forces. All right. So, naturally speaking, what happens is that none of these springs are perfectly frictionless also. So, when you are stretching and when you are leaving it, you realize every time you keep on doing this, with time you see springs will start becoming a less and less, ideal. Because if you imagine, if you take a spring and keep doing this, keep stretching it again and again and keep leaving it. After some time, you will realize that if right now, if I stretch it, it comes back perfectly. After some time, if you keep doing it, it will not come back to the original length. When you elongate it and leave it, it will only come back partially. So normal springs practically will, wear out with respect to time. However, ideal springs, we ignore all these effects. Okay. Can you suggest me a physics teacher on an Unacademy app who would teach 90% in English except you? I have no idea, Sabrish. I have no idea. If I don't know much about, the teachers that are teaching. Maybe you can search if there is somebody. Okay. All right. So remember that in ideal springs, these are hypothetical, theoretical, quantity, substances. Okay, these are not real springs. So ideal springs, we will consider that none of this is happening. Whatever will happen to the real spring, you can stretch an ideal spring indefinitely. Okay. Okay, so you can stretch an ideal spring indefinitely. There is no problem. You can elongate it as much as you want. Similarly, theoretically, you can make the length of an ideal spring as 0 also. Okay, so if the spring has a natural length of L0, the maximum compression allowed would be L0 only theoretically. Theoretically, for ideal springs, their length can become 0 also. All right. Okay. Okay. Anyhow, so as I was saying, so please remember all your strings that you are considering are ideal. Ideal strings can be stretched to any amount, can be compressed to any amount. Ideal springs do not have friction or any wear and tear out forces. Okay, ideal springs are also massless. Okay, so remember that. So maybe I can write it down. Properties of an ideal spring. Okay, so maybe I can write it down here. So properties of ideal springs. So please pay attention to this. Good afternoon, Krishna. Yes, I know. I can see that you are late. It's all right. It's all right. Try not making that a habit. All right, you should be in time. Okay, Sabrish, as I said, there are not too many teachers, who are teaching in English. So that is why Unacademy had to go out and look for new teachers. That is why they got me on board in July only when they planned of launching this JEE English channel. Okay, so trust me. I mean, before this, I was also teaching in Hindi only. All right, I've been teaching all my life in Delhi only. So yes, so I have also been teaching in Hindi, but yes, I can teach in English also perfectly fine. So there is very few teachers who can do that. That is why Unacademy also had a problem, but they still wanted to get teachers who can teach completely in English. So that is why they already had so many teachers with them, but they had to go out and look for new teachers for English. Okay, so that is going to be a little difficult, finding a teacher who is teaching completely in English. Okay, it's slightly difficult. All right, now properties of an ideal spring, as I was saying. So first is their minimum length. Their minimum length can be zero. Can be zero. So that's the first important point. There are also English batches in Plus platform. Yes, there must be. There must be some. I'm sure. Okay. So that is the first property, that the minimum length of an ideal spring can be zero. All right. Second is their maximum length. Their maximum length can be infinite. Theoretically, it can be. You can stretch theoretically a spring up to infinity. Okay. Want to see you speaking Hindi? Okay, उसमें क्या problem है? अरे भाई, I keep telling you guys, my mother tongue is Hindi. I have been teaching physics in Hindi. Okay, so let me say one sentence in Hindi. Okay, so देखो स्प्रिंग की एक खास बात है, दैट स्प्रिंग आइडियल स्प्रिंग का लेंथ जीरो करने में कोई प्रॉब्लम नहीं है. रियल लाइफ में ऑब्वियसली वो जीरो नहीं हो सकता, बट an ideal spring can be reduced to zero length. Okay, does that work, Mr. Solutionist? खुश? अभी समझ में आया? Okay. Next thing, obviously, an ideal spring will always keep on following the Hooke's law. Okay. In real springs, the problem is, as I said, over a period of time, every spring will get damaged and it will stop following the Hooke's law perfectly. All right. But an ideal spring will always follow Hooke's law no matter what. So an ideal spring, ठीक है, तो आइडियल स्प्रिंग हमेशा ही हुक्स लॉ फॉलो करेगा. ओके ओके, सो एन आइडियल स्प्रिंग will always follow Hooke's law. All right. Okay, so these are some properties. Again, ideal springs have no friction or wear out forces. Ideal springs have no friction or wear and tear forces, or they don't essentially get worn out. And finally, idle springs are massless. So remember, whenever we are studying idle springs. So we make these assumptions. Okay, please remember this. Okay, let's go over all the assumptions that we are studying our springs under. So the first assumption is that the minimum length of this such a spring can be 0. The second assumption is that the maximum length can actually be infinite. Theoretically, you can stretch an idle spring up to infinity also. Now, an idle spring will always follow Hooke's law. Okay, it never stops following Hooke's law. In real life, obviously, over a period of time, you know that every spring gets damaged, will not be able to follow Hooke's law eventually. For some time, it will behave as an idle spring. All right, it will always follow this law. But then after a point of time, when over extensive usage, there will be wear and tears of these springs due to some friction between their parts and other internal wear and tear forces. So in ideal springs, all these forces are absent. There is no friction between their parts, and there are no wear and tear forces, so they don't get worn out. Finally, idle springs are massless. Okay, so we do not consider the mass of any springs that we are studying. Okay, so these are the properties of idle springs that you must remember. Next, we will talk about parallel combinations of springs. So you can also combine two or more springs to form a single unit. Okay, and two most common ways of combining springs are parallel combination and series combination. So all right, let's talk about parallel combination first. Okay, so yes, this is where you can see this entire thing. So suppose there is a wall. There is one spring like this, there is another spring like this, and then there is another spring like this. All right, so you have a mass connected to this. So this is called a parallel combination. All right, this is called a parallel combination. Only when in elastic limit real springs follow Hooke's law. Yes, Pawan is absolutely right. That there is an elastic limit for real springs. Only you need to stretch it only in that limit. Now, as I was saying, Pawan, even in that limit, it will stop following Hooke's law after a point of time, after enough wear and tear. Okay. So now this is what you call parallel combination. So let's imagine that all these three springs have some spring constants. Let's call the spring constant of this K1, let's call this K2, and this has a spring constant K3. Now, when I want to find an equivalent spring constant, what I mean is that instead of all these three different springs, what happened if I could combine one spring, and what should be the K of that spring? All right, so this spring, if I could replace all three with a single spring such that the effects produced by three springs are exactly replicated by this one spring, then the spring constant of this is called the K equivalent. So this has a spring constant which is called K equivalent. So K equivalent essentially means that you should be able to replace all these three springs by a single spring. All right, now let's see what we are trying to do. So when I stretch this by x, okay, so imagine that this body gets stretched by x. All right, so this has moved by some x. Now, what do you want? You want a force. You want to calculate the force that all the springs are applying on it. And similarly, it should be the same when you stretch this body by x. So if in both the systems, when I stretch my block by x, if it feels the same force, then I can say this one spring is equivalent to all three springs combined. All right. So let's try it. This should also feel the exact same force F. Now in case number one, let's call this case number one, this case number two. In case one, what will you see? You will see that this F would be the summation of forces applied by all three springs. So the first spring would apply K1x, the second would also apply K2x, and the third will apply K3x. Alright, these are the forces that are being applied by different springs. Alright, and the net force that the block would feel would be the spring force due to first spring force due to the second spring, and spring force due to the third spring. Alright, now you also know for case 2, this F would be equal to K equivalent times x. Now all I need to do is equate these two. When I equate these two, what do I get? Let's see. On equating, the two, I am getting that K equivalent is equal to K1 plus K2 plus K3 and so on. However many springs I would have applied, the K equivalent, all those springs in parallel combination can be replaced by a single spring which will have a K equivalent of this. So this is my final formula for finding the K equivalent of 3 springs. Again, I could have done that for as many springs that I feel like. So please remember this, that this is a formula which is very similar to the formula that you studied for parallel combination, series combination of resistors. So here for springs, you are getting a formula for combination which is same as series combination result for resistors. You will realize some more things about this, that in parallel combination, every spring gets elongated by an equal amount. Alright. Yes, this is one example. This is here, 3 springs connected like this. Alright, I will give examples, more examples also of this. Don't worry, I will give you a problem to solve. Alright. So one thing that you can note is, so let's write a small note also at the bottom. So remember this, in parallel combination, okay, so in parallel combination, okay, all springs undergo equal deformations. However, they are all applying different forces, but apply different forces. So please remember that. I will have a question over this, okay? Arpit, don't worry. Alright, so this is everything that you need to know about parallel combination of springs. So the K equivalent is nothing but the sum of the individual spring constants, and in parallel combination every spring undergoes equal amount of deformation, that is either elongation or compression. However, every spring individually is applying a different force, okay? Next, let's talk about the series combination of springs. So what is series combination of springs? So we call springs in series combinations if you have springs connected like this. So this is one spring, then this is another spring, and then this is the third spring. Alright, so imagine you have 3 springs connected like this to a mass. So the first spring has a spring constant of K1, the second has a spring constant of K2, third has a spring constant of K3. Alright, so imagine 3 springs, they have been connected in series with each other. Alright, hi Chinmay, how are you? And I want to find the equivalent of this. Then again, what do? I will replace this with a single spring. So I will replace this entire thing with a single spring, and the aim is to find the spring constant of this. So spring constant of this single spring, which could replace all the 3 springs, is called the K equivalent. Alright. Now the idea again is the same only. The idea is same. If I stretch this by x, so imagine if this gets stretched by x. So let's draw that by red. So imagine that this block shifts here and this shifted by x. So it should feel a force of, let's say, some F force it is feeling due to all these 3 springs. Your single spring also, when shifted by x, should apply the same amount of force. Again, if I shift this also by x, this should also apply the same force F. So that is the idea. That is the idea. I need to calculate the equivalent spring constant. Alright. So how do we do that? Let's see. Now here I use a trick that if you look at these points, just focus on these points. Focus on this point and this point. Alright, on these points, what has to be the net force? the net force has to be zero. Why? These are points of springs, and the points of springs are massless. So if this is a massless point, the force by this spring here should be equal to the force by this spring here. That is the trick that I am going to be using. So let me imagine that if I connected these three springs and I stretch the end by x, then individually all these three springs would undergo different elongations. So let's say this gets elongated by some x1, this gets elongated by x2, and this gets elongated by x3. Now the trick that I have to use is that if I focus on these points, the joints of the springs, they should have a net zero force because they are massless. If they are massless, the spring force due to the spring on the left hand side, which is pulling it towards left, should be equal to the spring force due to the spring on the right hand side, which is pulling it towards right. All right, so let's name these points. Let's name these points some A and let's say some B. All right. Okay, so then what you will get is that you can write two equations from here. First thing that you can say is if the first spring got stretched by x1, second got stretched by x2, third got stretched by x3, then x should be equal to x1 plus x2 plus x3. So what will be the total amount of stretching? Total amount of stretching you will find would be this. Okay, I hope you can see that. Is that understood? Next, I will talk about point A. So for equilibrium of point A, the net force has to be zero, right? So the force on this side should be equal to the force on this side. So I can say the force on due to here, let's call it Fs2, and the force here, let's call it Fs1. So spring force due to spring 1 should be equal to spring force due to spring 2. Now spring 1 got elongated by x1. So I know Fs1 would be K1 x1. Similarly, Fs2 would be K2 x2. And since this is a massless point, imagine this is a massless point. So since this is a massless point, the net force can only be zero. All right, so let's write that also. Since A is a massless point, I can say net force on it must be zero. All right. So if I apply this condition, then I can say K1 x1 should be equal to K2 x2. Now similarly, I can say for B, for point B, I can say that what are the forces on point B? Point B, one spring is stretching it towards this direction, which is Fs2, and this spring is pulling it in this direction, which I am calling Fs3. So Fs2 should be equal to Fs3, which would imply that K2 x2 should be equal to K3 x3. Now let's talk about the point C also. Point C is the point that is connected to the block. Let's call this point C. So again, point C would feel a force of K3 x3 because it is connected to the third spring, and this force is F. This is the force F that the block is feeling. All right, so please also note. Okay, so let's write that. Also, K3 x3 is nothing but F, because K3 x3, that is the point. The point C is the point that is connected to our mass. Point C is a point of spring 3. So spring 3 would be pulling it with K3 x3, where x3 is the elongation in spring number 3. So please remember that. So I have all these relations. So from here, what all can I say? From the above equations, from the above relations, what can I say? I can say that x1 equals F over K1, x2 is F over K2, and x3 would be F over K3. All right, I hope you can see that. See, K1 is equal to K1x1 equals K2x2, K2x2 equals K3x3, and K3x3 equals F, which means all this, even K1x1, this is also equal to K1x1, this is also equal to K2x2. Alright, so once I have that, I can say that x1 is nothing but F over K1, x2 is nothing but F over K2, and x3 is nothing but F over K3. Now let's look at this. Here, for this spring, what can I say? For this spring, if I look at this point is connected to this single spring, the elongation is again x. So here, I can say for point D, for D, I can say that F is equal to K equivalent times X. Alright. So from here I also know X is equal to F over K equivalent. So I got these equations. I got the expression for x1, I got the expression for x2, I got the expression for x3, and I got the expression for x. Now let's substitute all of these here. So if I substitute all of these here, so substitute all of these in equation number 1. So let's call this equation number 1. So this is my equation number 1. Now all you need to do is substitute all values, substitute all in equation 1. Let's see what that will give us. Alright, so when you start substituting everything here, x can be written as F over K equivalent. This should be equal to x1, which can be written as F over K1, plus x2 can be written as F over K2, plus x3 can be written as F over K3. You realize all the f's will get cancelled, and 1 over K equivalent would be summation of 1 over Ki. Alright, this is the final result. This is what you need to remember. That in parallel combination, in series combination of springs, you are getting the formula which was the parallel combination formula for resistors. Okay, this is the derivation of this. So please go through it and let me know if there is some part of this that you do not understand. Alright, so please go through all this. See how we got the formula for K equivalent. Now if I have n number of springs in series, now I can replace all n number of springs by a single spring having a spring constant which we are calling K equivalent. Okay. So please let me know if all this is, if you're following all this. Yes. So the formulae for combination of springs are in fact right opposite to the formula for combination of resistors. Okay. So I hope you guys followed this. This is the result that you need to remember here, and here you needed to remember this. K equivalent here is summation Ki. Alright, here it is summation of 1 over K equivalent is summation of 1 over Ki. Alright, now you will also note what is happening in series combination. In series combination, every spring is undergoing different deformation. However, every spring is applying the same force. So there you see is the difference. So here in parallel combination, all springs were undergoing equal deformations but applying different forces. Alright, and what is happening in this combination? So let's write that also. Let's make a note of that. Okay. So let's write a small note about that. In series combination, okay. In series combination, all springs undergo different deformations. But apply the same amount of force. They apply the same amount of force. So just remember these. These are small things that you need to remember. Alright. So that is everything that you need to know about these series combination of springs. Thank you, Samajit. Okay, so why don't we go ahead and solve a couple of problems? So, okay, I had only one problem here. So this says that a spring or spring constant K is cut into 3 equal parts, and all the 3 parts are then connected in parallel. You have to find the equivalent spring constant of this spring system. Yes, actually yes. The line thickness, I maybe if I select smaller, then that would be better. Hi Yasir, how are you? So why don't you try this problem, guys? So you have been told there is one spring which has a spring constant of K. Now it is cut into 3 equal parts, and all 3 parts are then connected in parallel. Okay, so no, that will not be the case. No, Pawan, the answer is not 3K. No, not K. Alright, Yasir, good to know. So you can follow this series of mine. No, 3K is wrong, Pawan. 3K is wrong. 3K is wrong. 3K is the wrong answer. Okay. Yes, yes. So what will be the K1 and the K2 and the K3? The K's of shorter parts would not remain K. You need to remember that. Okay, let me show you how. The answer is 9K. The answer is 9K. Yes. Yes, Chinnu. Okay, yes, you have got the right answer. That is the correct answer, 9K. So, okay. Oh, that is strange. Imagine now, if I have one spring, and if I cut it into 3 equal parts, now you realize that I can think of this as a series combination of 3 springs. I can think of my one spring as nothing as series combination of 3 springs. So let's say that this has a spring constant K dash, this also will have K dash, this also will have K dash. Why? All 3 parts are equal. Alright, now I know 1 over K is 3 times 1 over K dash. So from here you get K dash equals 3K. Alright, every part will have a spring constant of 3K. Okay. Oh, hi Mahendra. Oh, great. By the way, guys, Mahendra, I think, is a class 10 student. Yes, you should be active too when you are studying. So that is why I try to stay very active. So if your teacher is active, hopefully you will also remain active. Okay. Thank you, Rishabh. All right, Mahendra, I think Mahendra, you are in class 10th, right? So now, of course, when you're when you're adding them in parallel combination, all right, so this has K dash, this has K dash, this has K dash. Now you know that K equivalent would be 3 times K dash, which is 9 times K. So 9K is the correct answer. Yes, imagine Mahendra has just completed his 9th and he is studying his class 11th topics. So you guys should be, learning a few things from Mahendra. And I hope you realize the level of competition these days. That students who have just completed their class 9th are already studying class 11 syllabus. So I hope all of you are very, very, very serious about your studies, because you need to be competing with students like Mahendra also. Okay. So please let me know if everybody followed this. Please let me know if everybody followed this. Is this clear to all? Is this clear to all? Thank you. Okay, what's wrong with Pawan? Okay, so Pawan, I guess, don't worry Pawan, you are not going to be taking the JEE with Mahendra, so you can relax a bit. All right, now let's discuss something else. What happens if I cut a spring into two parts of one third? So one third length is here and two third length is here. So this is two third length and this is one third length. So what will be the spring constants of these parts now? Please tell me, what do you think would be the spring constants of these parts? If a spring has been cut into two parts of one third length one side, two third length on the other side, then what are going to be the spring constants of these two parts? So you have to find the K of this part. So let's call this as K1. So K1 and finally K2. So find me K1 and K2. Okay. So let's say this as K2. And the original spring had a spring constant of K. If the original spring had a spring constant of K, what will be the values of K1 and K2? Which are essentially the spring constants of these two parts. All right. So, not 1 by 3K. Yes. Amy has got the right answer. It would be, no, 3 by 2K and 3K. 3 by 2K and 3K. Okay, 3 by 2K and 3K by the way. So again you can do that only. You can consider that I cut this first in 3 equal parts. So let's imagine I cut this into 3 equal parts first. Now each part should have a spring constant 3K. So that gives me the answer for K2 straight away, that K2 would be 3K. Now K1 is nothing but a series combination of two springs of 3K and 3K each. Alright, now I can think that K1 was nothing but series combination of two springs of 3K each. So yes, absolutely. So K1 would be 3K over 2. Alright, so these would be your answers. K1 would be 3K over 2 and K2 would be 3K. Hi Vineet, how are you? So now I hope you can find the spring constants of any such parts. If a spring is cut in any such parts. Alright. Do you want one more? Do you want one more of such problems? So let's say you have a spring. Okay. And I'm cutting it into, this spring has a spring constant of K. This spring constant has a spring, constant K. And how many parts do I cut this in? Okay, so let's say I am cutting this into, okay, two parts again, let's say. I'm cutting this into two parts. So one is 2/5 of the length, 2 by 5 length, and another is 3 by 5. So these are the two parts that I have cut my spring into. So one is 2 by 5, one length is 2/5 of the original spring, and the second length is 3/5 of the original. What will be the spring constants of the two individual parts? So find the spring constants of the spring individual parts. Yes, so yes, Mahendra has immediately given me the correct answer. Yes, absolutely, this part would have a spring constant K dash equals 5K by 3 or 5K by 2, and this would have K double dash as 5K by 3 also. Alright, so yes, okay, so I'm guessing now you guys are getting a hang of this. If we cut a spring into various parts, you should be able to find the spring constants of all the parts. Alright. So if everybody has understood this concept, this idea, then should we move forward? Is this idea clear to all you guys? Judging from your answers, I have a feeling that you guys are getting a hang of this. You guys should be fine. So please let me know in the chat also that if this idea is clear, or do you want me to discuss maybe more problems. Arpit was saying that. All right, so Arpit has also got, Amy has also got. So wonderful. Let's move ahead now. Now let's talk about something very important. This would help you in solving your problems. So this part is called making the free body diagrams. So what is a free body diagram? Free body diagram consists of a diagrammatic representation of a single body or a subsystem of bodies isolated from its surroundings. Yes, absolutely. Absolutely. Okay, very well said. Yes, Mahendra is absolutely right. Okay, so coming back to FBDs. So FBD or free body diagram is nothing but a diagrammatic representation of a single body or a subsystem of bodies isolated from its surrounding, showing all the forces acting on it. So what essentially is a free body? So free body is something which is not in contact with anything. Alright, that is what I mean when I say free body. Free body is something which is not connected to anything, which is not touching anything. Alright. So when you have to make free body diagram, so what you do is, what are all these contacts doing? What is any of the contact doing? So this guy is touching this here, is touching this here, and is also feeling a force of gravity due to the presence of Earth. So if I had to make an free body of this, so first of all, I have to remove this from every other thing that it is close to or interacting with. Now, all the interactions can be simply replaced by the result of those interactions. Alright. So what is this interaction going to do? This interaction is going to produce an N. So one, I will make an isolated body which is not touching anything, and I will represent all the results of the interactions by the forces that every contact is causing, or every non-contact interaction is causing. So here I will see that this is touching two objects, two surfaces here and here. What does this surface do? So the effect of this contact would be an N. This contact would apply a normal reaction on my sphere. Alright. Similarly, this contact would apply another normal reaction, so which I am calling N2. And finally, the interaction with the Earth would have caused a force of mg. So this is what you call FBD. Alright. Now, in FBD, you generally represent all bodies with point masses also. So the technically correct FBD would be this. You will represent this by a point mass. You will have mg, you will have N2, and you will have N1. Again, the directions, please note, would be corresponding to this only. So you will find the direction by knowing that this N has to be perpendicular to this surface. So the directions are always marked proper, okay, in this FBD. So this is the final FBD. This is the final FBD. In the final FBD, you always represent any object with a point mass. Alright. So I hope everybody follows what FBDs are. FBDs are nothing. You are isolating the object. Now you are identifying the effect of each contact that it had and each interaction, even non-contact interaction that it had with other things. And you are just simply representing all the forces acting on it. So this is a body which is not touching anything, which is not connected to anything, and it will have these forces acting on it. This is what FBD is. Alright, now please note that drawing FBDs correctly is the key to solving all the NLM problems. So if you can draw all your FBDs correctly, then trust me, solving the problems will not be an issue. So this should be practiced a lot. So let's see. Let's draw the FBDs of each of the following masses. So you have these three conditions. So you have to draw the FBDs of M1. Okay. Draw the FBDs of M1, M2. Here you have to draw the FBD of M. Here you have to draw the FBD of this M. So draw the FBDs of all the masses. Do it in your pen and with your pen and paper. Then I will discuss it here, and let's see if you are making the right FBDs. Alright. So again, the steps of making an FBD would be identify all the contacts, identify all the non-contact interactions, and replace all the forces arising through these contacts and the non-contact interactions, and apply them on a point mass. Okay, these are the steps of making an FBD. So maybe I can write it here. Maybe I can write it here. So let's just write steps of making an FBD here. Alright. So steps of making FBDs. So please follow these steps and you will be fine. So the first step is, okay. So the first step is, number one, identify all the contacts that a body has. Okay. Step number two, when you have identified the contacts, you have to identify what are the forces arising from these contacts with proper directions. So identify. So second step is identify the forces arising from these contacts with proper directions. All right. Third, identify all the non-contact interactions that it has, because there might be non-contact forces also acting. So identify all the non-contact interactions and the forces arising by them. All right, finally, represent the body or system So first you will also identify a system, okay? Okay, so represent the body or the system as a point mass and show all the forces acting on it Oh, by the way, isolated point mass. So show it as an isolated point mass. So it should be separate now. Now it should not be in touching anything or in contact with anything. It is supposed to be isolated. It is supposed to be away from everything. And now show all the forces acting on it with proper symbols, with usual symbols and proper directions. So those are the steps that you need to follow while making an FBD. Alright, so please remember, just go through these steps. So first what you do is identify all the contacts that a body has. Second, you identify all the forces arising from these contacts with proper directions. We have already spoken about the directions of all the contact forces that you will be coming across. So those were normal reaction, tension, spring force. Now, since you have studied about all of them, you should know how and where these forces act. Alright. So once you have identified that, finally you identify all the non-contact interactions and the forces arising due to them. And finally you represent the body or any system as an isolated point mass, and show all these forces acting on it with usual symbols, which is generally for a normal reaction you will use N, for tension you will use 2, T, for spring force you will use Fs. Okay, so use these symbols so that you are clear about which force is arising from what kind of interaction with proper directions. That is what you do. You don't have to find the values, you just write it as symbols. Okay, That is all that is needed to complete your FBD. Okay, so Sabrish, what is the need of writing FBD? Okay, so FBDs are very helpful when you're applying the second law equations. All right, FBDs will help you apply the second law equations more effectively. We usually follow a standard procedure for applying Newton's second law and finding all the equations to get all the answers. So FBD is just a standard method of application of second law. Okay, this is used in that. Can you say 10 Hindi words and their meaning that every educator uses during the lecture? Okay, I have no idea what 10 words every educator is using in their lectures. I mean, that will depend on the topic. No, Sabresh. I don't know, if I'm teaching electromagnetism, I may be choosing different Hindi words, and if I'm choosing mechanics, I may be choosing different Hindi words. Some of the very commons are, okay, samajh aaya. Samajh aaya means, did you get it? That is one probably a very, very common word that any teacher would be using. Or are you following? So samajh aaya means, are you following, or did you understand? Okay. Rest, obviously there is no fixed 10 words that are only used, okay, while teaching. I mean, it's up to the person who's teaching. He can use any kind of words. So why don't we get back and draw the FBDs of each of the following masses. Now, I hope you have noted down these steps. So do you have to draw the arrows with the head pointing? Yes, absolutely. Absolutely, look at this. You have to specify, see, all forces are vector quantities. So they are to be specified with the correct directions. So I am specifying all the forces as proper vectors. Okay. Then theek hai. Okay. Theek hai means alright. Theek hai means alright. Okay. So please note down these steps. Okay, please note down all these steps. And this is what you will follow while making your FBDs. Alright. So I'm giving you 1 minute to note down all these steps. Alright. So hurry up and note down all these steps. And we will see the use, Mahendra. We will see the use. Why, making FBDs. Trust me, making the correct FBD is half the problem solved. Alright, when you're applying Newton's second law. In the application of Newton's laws, half the battle is won if you have drawn the correct FBD. Then there is maths only. Okay, so hopefully you have noted down all these steps. Now let's remember those steps and draw the FBDs of these. All right. So please try making the FBDs of these and let me know in the chat when you are done with this, when you have drawn your own FBDs. And then I will also draw the FBDs, correct FBDs, and show you the correct answers. So draw your own FBDs, then I will start drawing the FBDs. And you can check if you drew them correctly. Alright, so I hope you guys are all making your FBDs. So make your FBDs quickly, following those steps. Alright. And then let's see if you are making the right FBDs or not. Okay, so this was supposed to be F. Here, this was F, if I am not mistaken. Yeah. So let me know in the chat when you have made your own FBDs. Okay. And then I will show you the correct FBDs. Okay. Guys, write something in the chat. Are you trying to make your FBDs or have you completed your FBDs? You will have to let me know. So get a pen and a paper, make your own FBDs on your pen and a paper according to what you think how it should be. And then I will show you the correct FBDs. Okay, so either everybody is busy drawing their FBDs or they think this is too simple. Okay, no problem. Here you have to draw the FBD of M1 and M2. Here you have to draw the FBD of M. Here you have to draw the FBD of this small m. All right, so since yes, you don't really have to say I will make, just check if you have drawn it correctly. So here obviously when I'm making the FBD of M1, I need to identify what the contacts are. So M1 has a contact here and M1 has, okay, so let's use some other color. So it has a contact here and it has a contact here. So both these contacts, what are these contacts? These are solid contacts. So what kind of force will they produce? They will both produce normal reactions. Now normal reactions would be push forces in the mutual perpendicular directions. So how about this contact? So let's take a look at this contact. Here the direction of mutual normal, common normal would be along this direction and the push would be upwards. Alright. So this should feel a normal reaction upwards due to this contact. Alright. Similarly, if I talk about the contact here, this is again a solid contact. This should again produce an N and that N should be again along the common normal. So again the common normal is along this line. Now M1 should feel a push. So M1 should feel a force in this direction. Alright. Now these are the only contacts that M1 has. Now what are the non-contact interactions that M1 has? It would be the interaction of gravity. It will feel a weight. So weight obviously we know is always vertically downward. So it will feel another force which would be due to gravitational interaction with Earth and that would be vertically downwards and mg. So once I have identified all the contacts and all the forces arising through the contact, now let's make the FBD of M1. So the FBD of M1 would look like this. So I will represent M1 as a point mass. So this is FBD of M1. Okay, so M1 would look like point mass and it would have a force of gravity which is M1G. Alright, then a normal reaction from the ground, let's call that N1. And then another normal reaction downwards due to the upper contact. Okay, so I am going to choose another color for that. So here it would have N2 also. So this is the FBD of M1. It has N1 acting upwards. N1 is the normal reaction between the ground and the M1. Then it has N2 acting downwards. N2 is the normal reaction due to the contact of M1 and M2. And finally it has the force of gravity which is mg. Now similarly when I am trying to draw the FBD of M2. On M2 again you will have a normal reaction which would be push again. So it should feel, this guy should feel a normal reaction in this direction. And of course this guy will feel the force of gravity. Alright, and from third law, if this guy feels a downward force of N2 due to M1, then due to M2, then M2 will feel an upward force of N2 only. Alright, upwards. So this is from the knowledge of third law. From third law, I can say if M2 is pushing M1 by N2, then M1 would be pushing M2 by N2. So FBD of M1 would look like this. So let's draw the FBD of M2. So M2 would have M2G and this would also have an upward force which would be N2. So this is along the common normal pushing it upwards and it will have a magnitude which will be equal to N2. Notes milenge? Yes, the PDF that I'm using here would be available for download. Alright. Comment master. So don't worry, you can download the PDFs. But it's always better to also make your own notes. Okay. Yes, comment master, I said notes mil jayenge. Don't worry. Don't worry. The PDF that I'm using here, everything that I'm writing on it also would be there available for download. Okay. Alright. Now let's take a look at capital M. Alright. Okay. So what are the contacts that capital M has? So let's identify all the contacts that this guy has first. So it has a contact here with the ground. Alright, this is a solid contact. So it will feel a push, a normal reaction. The normal reaction would be along the common normal. This is the common normal. Alright, and then it will feel a push, so has to be upwards. Alright, now here it has another contact. This is a contact with a string. So what does string do? Strings apply a tension force which is always a pull force along the length of the string. So this will cause a tension force which is in this direction, it will be a pull force along the length of the string. So I can call this T. And finally, it will have gravitation. Oh, it has another contact here. So this is an external agent applying a force. So obviously the direction and magnitude of this F already has been given. So these are the three contacts that M has. One with ground, one with a string, and one with an external agent. So from ground, it has N, which is pushing it along the common normal. From string, it has T, which is pulling it along the length of the string. And external agent already is pulling it in this direction as shown. Finally, it has gravitational interaction with Earth. Yes, okay. Okay, so what we can do is, by the way, we haven't had a quiz for kinematics. Okay, so maybe I can keep a quiz on kinematics, but the only problem is I like to conduct quizzes on Sundays, but this Sunday I am really busy because I have a long lecture planned on the Plus app, which will have rotation revision, okay, revision of rotation. So yes, I will plan a Minty quiz. I haven't taken any Minty quiz for kinematics also, so maybe I can plan next week. I can plan a mega quiz for kinematics, and then we can have a small quiz on, all the NLM parts that we have covered. Maybe next week. Okay, I will be planning these. Now, once I have identified all the contacts and every force that should be arising from this contact, all right, I can plan either of those. Yes, I can plan a quiz on the app also. All right, don't worry. I will plan one of those next week. Okay, so this week again, as I said, because the 2020 people have their JEE coming up, so I have planned some mega revision sessions. Okay, very long revision sessions for them. All right, last minute revision sessions if they are interested. So next week I will be most likely free, and then I will conduct these. So let's get back to drawing the FBD of this guy. All right. So this guy, first of all, let's represent him with a point mass. So this is S. Now all the forces that I'm identifying is, one is mg first of all, which is due to the interaction of a force of gravity arising due to its non-contact interaction with Earth. Another, from this, it has an N. So let's call it N. Because there is only one N, so I don't use subscripts of 1 and 2. Okay, I can only write N because there is only one N. In this case, when we had more than one N's, then we write N1, N2, and N3. So N would be upwards, all right, along this direction and pushing it upwards. Next, you will have F. So F would be in this direction, and finally you will have a T, tension force, in this direction. So this is the FBD of capital M. All right. Finally, now let's draw the FBD of small m. So small m, let's identify again the contacts that it has. So it has a contact here, it has a contact here. These are the only two contacts that I can see. Now, take a closer look. This is a solid-solid contact. This is a solid-solid contact. So this will give rise to a normal reaction. Normal reaction has to be along the common normal. So the common normal is this. And the force that this small m will feel would be push force. So it will have a normal reaction in this direction. Now this is a string. Strings always pull. So from this string, it should have a force in this direction, which we will call T. This we will call N. And of course, then you have mg. So mg obviously would be acting like this. So these are all the three, two contacts and one non-contact force that I can see acting on small m. So now let's draw the FBD of small m. So FBD of small m would look like, so this is small m. So first of all, we draw this mg. Then you draw a tension force, which is along this direction. And then you draw a normal reaction, which is perpendicular to T. Okay. So this is your N, this is your T, and these would be perpendicular. And you can also say that the direction of T, this would be theta. All right. It would be along the length of the incline. So these are the three FBDs. Please take a look at them and let me know if you made the right FBDs. And in case you drew the wrong FBDs, then hopefully did you follow that this is the correct, these are the correct FBDs. All right. Please let me know if you are clear about this. Then I will move on to the next slide. Are you guys clear about these? Are you guys clear about your FBDs? Trust me, you should be very familiar with drawing FBDs, and you should be always drawing the correct FBDs. As I said, in Newton's laws questions, if you are able to draw the correct FBD, that is half the problem solved. Okay. All right, Mahendra. Good to know that. How about others? How about others? Have you made the right FBDs? All right, great. So most of you have made the correct FBD. So let's move forward and practice some more. All right, so these are the kind of situations that will be given to you in questions. Okay, so you have to draw the free body diagrams of each of the following masses. So in this case, you have to draw the FBD of this. In this case, you have to draw 3 FBDs, by the way. You have to draw FBD of this, FBD of this, and FBD of this. In this case, you have to draw FBD of this, FBD of this. In this case, you have to draw the FBD of the man and this ladder. Okay. So essentially, 1 FBD here, 3 FBDs here, 2 FBDs here, and 2 FBDs here. So once you've made all these FBDs, I think you should be sorted with your FBD making. Okay. Consider all pulleys and springs and strings to be ideal. Okay. Consider everything to be ideal. All strings and springs to be ideal. Okay. So please draw these. So you have to make a total of 8 FBDs here. Will there be tension in second case? You think about it. You tell me. Sir, I was watching you non-live classes till now and very often I was getting bored. But today I am attending your live class and live mein time ka pata hi nahi chalta. So that is why you should be attending more classes live, Arpit. Live classes can be more interactive, right? That is why we pitch in and tell you that you should be opting for your Unacademy courses, plus courses. What are the benefits of those? I mean, every class will happen live there. So plus that will be even more interactive than this. So if you're having interactive classes, of course, you enjoy the class more, you learn more. So it is always better to attend all your classes live. If you've seen the video that I have made, that video was about, how to make the most of your online lectures. There I have suggested to students, if you want to make the most of your online lectures, attend them live. Okay. All right. So please make the FBDs of these. For non-live lectures, you can maybe watch it at 1.5x speed. There will be spring force, but no tension. Okay. Okay. In which one? In the second one, I don't know which you're talking about. So just draw your FBDs, and let me know in the chat once you are finished drawing all these 8 FBDs. So take your pen and paper, draw these FBDs. Once you're finished drawing all these FBDs, let me know. I will draw the correct FBDs. All right. Second case, of course there will be tension. Of course there will be tension. Of course tension will be there. If there is a string which is not slack, there will always be tension. Okay. Okay, Mahendra. So Arpit is done. Let's give 1 more minute to others. Okay. So Mahendra, remember this. Whenever there is a string, unless it is slack meaning it is like this. As long as you have taut strings, string is stretched, then it will always have tension. Now, even if it doesn't have tension, your value of t will come out to be 0. But whenever anything is connected to a string, you have to assume the tension is there. Okay, remember. By chance, if the tension is 0, you will get that in your equations. You will get, when you solve your equations, you will get the value of t as 0. Or if you get the value of t as negative, then also you know the tension cannot be there. By default, you have to assume the tension is always acting. Okay. So Arpit is done. How about others? Let me know once everyone is done. Alright, I am giving you 1 more minute. So 30 more seconds. Then I will start discussing this. Okay. Hurry up if you haven't drawn all the FBDs. Hurry up and draw them quickly. Okay. Let's see. All right. So let's start. So first of all, let's talk about this. Here the forces are already shown, by the way. So this has one interaction with the string, another interaction with this string, and another obviously gravitational interaction. So when you're drawing the FBD, this should be very easy. The FBD of this would be, you will draw this as a point mass, you will apply an mg, and then along the lengths of the strings. So if this string is going at some angle alpha and this string is going at some angle beta, then you will draw at alpha, you will draw some T1, and also at beta you will draw some T2. So please remember, always draw your FBD showing forces in the correct direction. So this will be the FBD of this. Now let's talk about here. Let's call this 1, this 2, and this 3. So now let's talk about 1. What are the contacts that 1 has? So 1 has a contact here and 1 has a contact here. This is a solid contact which will give rise to an N. It would be along the common normal, which is this. It will be push, which is this. So it will cause, let's call this N1. So it will feel an N1 because of this solid contact. Then there is this string will pull it. It will pull it along the length of the string. So you have this. So this should give rise to a tension. And so these are the two contacts taken care of. And finally, of course, you should have the mg. So m1g. Let's call the mass of this m1 and let's call the mass of this m2. All right. So now while you're making the FBD of 1, let's see. So FBD of 1, what does that look like? So that will look like, first you have mg, then you have t, and then perpendicular to t you have n1. Alright, so mg, t and n1. So please remember the direction of t would be at alpha with this, and this would be 90. Alright, so this is what the FBD of 1 looks like. Okay, now let's talk about the second. The second has only one contact with a string. So there is only one contact force arising. Now you need to remember that I told you, consider all your strings to be ideal. So if this string is ideal, what are the properties of ideal strings? That they have the same magnitude of tension everywhere. So the tension here would be again T only. You do not use different symbols for these, because you should know that this T and this T would be equal, because in one string, as long as the string is ideal, the tension is always same everywhere. So this you needed to remember. Now the FBD of this is very easy. Okay, so for 2 you have FBD as 1 M2G and another you have T. So that is it. Just remember that you use the same T that you use here. Now let's talk about 3. Now this would be tricky. 3 has a lot of contacts. So please remember. So I'm rubbing all the contacts due to others now. Okay. So I'm rubbing the contacts due to everyone else now. And I'm going to focus on 3. Alright, so 3 has one contact here. This is a solid contact. This would give rise to one normal reaction. This again is a contact. It is in contact with ground. So please remember, you also consider the contacts with ground. So this is again a solid contact. So this will give rise to a perpendicular push force. And since here I took it as N1, so I have to take this as N1 only. And this will again result in a push force which is perpendicular to this. So this push force would be N2. And now is the tricky part. Please remember that this pulley is also connected to this. So pulley will be considered a part of 3. Pulley will be considered a part of 3. Please remember this. Whenever you're drawing the FBD of this, you will consider the pulley to be a part of this. Now pulley has 2 contacts, one here and one here. So this will pull with T. This will also pull with T. So now when you're drawing the FBD, you have to make sure that you have identified all the four contacts, okay? Because you maybe mostly students miss out these, or maybe they can miss out this also. So now when you're making the FBD, let's consider the mass to be capital M. If the mass is capital M, finally I will have mg also. So the FBD of, okay, the FBD of 3 would look something like this. So first you will have capital Mg, and then you will have N2. N2 is pushing it here. Then you have N1. N1 is pushing it here. Alright. Now please remember that this angle would be alpha. This angle would be alpha. You can judge it from trigonometry, okay? I'm not showing how this is alpha. Now comes the tricky part, that you have to apply this and this also. So you have to apply a T which would be perpendicular to this N. Okay, so this entire angle should be 90. So one T acting here and another T which would act vertically downwards, which is this one. So let's draw that with some other color. So you also have another T here. So this would be the correct FBD of this. Okay, so this is N1, by the way. This is N1. This would be the correct FBD of 3. Okay, please let me know if you followed this. I hope you guys followed this. So these are the FBDs of 1, 2 and 3. If there are no more confusions, then I will move on to the next problem. All right. Hi Hemlata. Hi. You just have to write it once. I will respond. Don't worry. All right. Please let me know if everybody followed this. Hi Hemlata. Hi to you. All right. Which part, Ashwin? Which part? All right, Ashwin, please. Ashwin Rajsekharan. Which part do you want me to explain one more time? Okay, Joel, Jaren Joel, long time. Sir, when will you start your batches at Plus? As I said, I think most likely around 15th of September. The last, okay. So in the last part, when I'm making the FBD of capital M, I have to identify all the contacts that capital M has. And please remember, can we crack NTSC in 2 months? Okay, yes, maybe you can. If you already have a good foundation, that is, if you have a good understanding, you can follow some lectures that I'm taking here for basics of NLM and your topics of 9th and 10th. The basics you should be understanding. With that, you can theoretically, yes, crack it in 2 months. I myself was an NTSC scholar, by the way. Okay. So yes, I haven't said everything about myself in my introduction. I was also an NTSC scholar. I also cracked the NSEP, which is the National Standard Examination of Physics Olympiad, that is. Okay. So all right, coming back to this problem, so which Rajsekharan was asking. So if I look at this M, so capital M, I will have to consider this pulley also a part of this. Okay. NTSC Mahendra is National Talent Search Examination exam which you take in your class 10th. Okay. NTSC is National Talent Search exam. It's a very old exam. It has been happening for ages. National Talent Search Examination. It is conducted by the Government of India. I took this exam when I was in class 10th. It has 2 stages. Okay. So that is what NTSC is, National Talent Search Examination. In which year? I think it was in around 2000. Year 2000. You can give it in class 10th, Mahendra. You can write that exam in class 10th. Okay, so since you have just appeared, you've just cleared your class 9. So yes, this year you can, next year essentially you can give it. I think the first stage usually happens in November. So maybe in November this year. I don't know if they will be conducting it this year or not. But yeah. Okay, Arpit. Oh no, bro. That can happen. So don't worry, you work harder. These are all competitive exams. So not only do you have to perform well, you have to perform better than others. Yes, you could do that. You could do that, but not to a great extent. Only a few chapters. Only a few chapters. You don't need to bother about rotation and stuff. Okay, Himlata. Don't read rotation and stuff. They don't ask rotation. But Newton's laws, work power energy, those two you can read. Okay, the syllabus that you have covered in class 9th. All right. So coming back to this. So Rajshekharan, I was saying that when you are making the FBD of capital M, you have to remember that this pulley is also attached to this. So please remember that this pulley, okay, this pulley is also attached to this. This pulley is a part of M1. All right. So please remember this. So when you are identifying the contacts that capital M has, you have to remember that pulley is a part of this. So when you are identifying contacts, identify all the contacts that are there of M1 with anything, including the pulley. So one contact is here. This is the one contact, solid-solid contact, which is with block M1. Then this is another contact that it has with ground. All right, two contacts I've identified. Now the pulley has string going over it. So whenever string is touching anything, string will pull that. So string will pull this end with T, will pull this end with T. Strings pull with T along the length of the string. Okay, so remember that. Whenever strings are attached. Okay, I was also in ICSC, by the way. I also studied in ICSC board. But yeah, I have prepared all my subjects well. Alright, so that is why you have four contacts here. One with M1, one with ground, and two with the strings that are touching the pulley. Pulley is considered the part of capital M. Okay, just see classes of Rohit sir and Abhinav sir and crack IIT. Yes, hopefully you should be able to do that. Alright, next. Once I have identified all these, then making the FBD should be very easy. Let's talk about this contact. So when you're talking about this contact, okay, so let's say, when you're talking about this contact, this is a solid-solid contact. Solid-solid contact should give you a normal reaction force. Normal reaction force is always a push-only force. It is along the common normal. So this is what will arise from this. Alright, this is the result of this contact. Next, if you look at this contact, okay, so let's use some other color maybe. If you look at this contact, this is again a solid-solid contact. Again, a solid-solid contact would result in one normal reaction, which would be along the common normal. It will be push. So this results from contact number 2. Now, the third and the fourth contacts are with strings. All right. So these are with strings. So this and this. These are two contacts that it has with strings. So both these contacts will give rise to tension forces, which will be in the direction of the string and pulling it. String force is always pull only. Yes, Arpit, that is one of the reasons why my English is so good. I was also in ISC. So this and this are arising from these two contacts. And finally, I have MG. Okay, so I hope that makes it clear. Ashwin Rajshekharan, is the FBD clearer now? Do you follow the logic? You have to identify each and every contact. Even if the string is just touching, you have to assume that it is pulling. Okay. That is why I took this up. Okay, so first of all, you don't need to take any names and make any comparisons here. I will be teaching on the Unacademy also, and yes, you can join my courses there. That is a matter of personal choice. A lot of people may be comfortable with somebody else. A lot of people may be comfortable with me. That is why Unacademy is providing you so many options. Okay, it is providing you so many options so that you can choose one that you like. Okay, so don't worry. I will be joining. I will be starting my courses on the Unacademy also. Okay. Next, how about the FBDs of these two? So let's draw the FBD of this and let's call the mass of this as small m for now. So when I'm looking at this, what are the contacts that this guy has? So this guy has a contact here. This guy has a contact here. So I can see only two contacts. Now this force could have been a push or a pull both. Now I will just assume a direction. Please remember, in springs we are not sure whether the spring is pulling or pushing. So you can imagine any one direction. If the direction was opposite, you will get a negative value. Alright, so when drawing spring forces, you can choose any direction assuming a push or a pull. Alright, so here I will assume a push. If it's a pull, then I will get my answer as negative. Alright, so please. Alright. So now let's talk about this. So this should result from a spring force, and spring force would be along the length of the spring and it will be a push force. So Fs. So this is the kind of force that will be arising from this contact. Now this contact would have a normal reaction which would be in this direction. So let's call this N1. Alright. So these are the two contacts and these are the two contact forces that are arising. Next, obviously I will have Mg also. So if I draw the FBD of this, let us see. The FBD of this would look like this. So first of all, you have to draw Mg. So capital Mg. Then you have spring force. Okay, why does this keep drawing these lines? So then you have a spring force. Okay, I don't know why. And finally you have a normal reaction. I'm calling it N1. So this is 90 and this angle would be theta. So this is the free body diagram of capital M. Okay. Alright. Next, let's draw the FBD of small m. Now small m, please consider this again. That is why I'm taking these tricky cases, because you often miss out some things. This small m has three contacts again. So I am getting rid of these contacts. So now let's take a look at the contacts that small m has. One is this, and one would be this, because this is attached to capital M. So please remember that this will also be considered to be a part of small n. So you need to see the force there. Now, if the spring had a push force here, then the spring will also have a push force here. So remember this, either the spring pushes both the ends or the spring pulls both the ends. Okay. Next class would be on Monday. For 11th, all my classes are on Mondays, Wednesdays and Fridays at 4, and for 12th, all my classes are on Tuesdays, Thursdays and Saturdays. Alright. So please remember this when I am drawing the FBD of small m. Now FBD of small m would look like this. So it has three contacts. One here. Okay. I don't know where are these lines coming from. One here and one here. So this contact will give rise to N. Since here the value of N was considered N1, so this will also be N1. Similarly, this contact would also give rise to another N, let's call that N2, and this contact would feel a spring force which will be pushing this end. And finally, of course, you have Mg. So when I'm making the FBD of this, I have small mg, then I have N2. Okay, why? I have N2, then I have N1, and finally I have the spring force. Okay, and finally I have the spring force. So obviously this angle would be 90 and this angle would be alpha. You can check that. So this would be the FBD of small m. Okay. What is my native place? Okay, Lucknow, UP. My native place is Lucknow. This is the capital of UP, Uttar Pradesh. That is my native place. Now I've been settled for the past almost 17 years. I've been settled in Delhi, but this is my native place. Okay. Alright, so I hope you guys are all clear about the FBDs of this. Now let's talk about the FBDs of this ladder. So ladder has a contact here, has a contact here, has a contact here. Alright. So this contact would make a force here. This contact would result in a force here. So let's call this N1, let's call this N2. And here also, this is a solid-solid contact. So the feet of the person, you have to consider the feet of the person. Feet of the person would be like this. So the normal would be in this direction, N3. So please remember, these are the three contacts and three contact forces arising through all the contacts. How is it 90? Okay, that is because N1 is supposed to be perpendicular to this, right? N1 is supposed to be perpendicular to this. And Fs is supposed to be along this. So Fs has to be along this. And N1 is supposed to be perpendicular to this. That is why the angle is 90. Okay. Oh, I have been to Meghalaya. It's a beautiful, beautiful place. Alright. So I hope you got that, Deepika Soni. The angle is 90 because one force is along the incline, another is perpendicular to the incline. Okay. Is that clear, Deepika? Please let me know quick if that is clear. Okay. Now the ladder also may have some mass. Let's call this mass small m. All right, and let's call the mass of the man as capital M. So the FBD of ladder. So ladder would have small mg. Okay, so small mg acting like this. Then it would have N1 acting here. It would have N2 acting here. And then it will also have another normal reaction due to the man. So you will have another one here which is N3. So this is what the FBD of ladder would look like. So this is FBD of ladder. Alright, now FBD of man is very, very simple. It will have a normal reaction from here, so N3, and it will have its own weight. So FBD of man is very, very simple. The man would feel a force of capital Mg and then a force of N3 upwards. Alright, this is the FBD of the man. Alright. Yes, I know. I have been careful, don't worry. Of course. You should always, all of you guys should always take care of your health. So please let me know if you followed the FBDs of all these bodies and if there is no confusion. I hope everybody followed all the FBDs. Now you should take out your HC Vermas and look at all the problems. Just look at the figures and try drawing different FBDs. Alright, maybe do that for solved examples, because in solved examples they will show you the FBDs also. So practice some more FBDs from the solved examples of HC Verma. Alright. Okay. So this is it. I think we are running out of time. I have already overrun the timing of this session. So this is where we will wrap it up today. Next class we will start, Monday we will start the discussion of Newton's laws. So before the discussion of Newton's laws, you needed to know all this. So our preparation for starting Newton's laws is done. And finally, Monday we will start with Newton's laws. Alright, so I had planned this for today, but then as I said, I will be keeping this extremely slow. So this session, which is meant for class 11 students, I will be taking over things very, very slow, explaining each and everything from basics so that you are understanding every bit of it. So that is why we will skip the next part for now. We will take that up on Monday. Monday we will start the discussion from the first law of Newton. Alright, so that is my time for today. I am in class 10th. I solved HC Verma and IE Rudolph. Oh, you have solved both of them. Oh, that is great. Then why do you have a doubt that you will crack NTSC or not? I am in class, I solved HC Verma. So if you've already solved HC Verma and Rudolph, then you are good for JEE also. Okay, which book is best for physics? Okay, so for theory, see, a lot of people will tell you a lot of books. Okay, so everyone has different perspective. Alright. So for me, I consider that as far as your theory is concerned, you should only refer to your theory from some standard text. Standard text meaning they will have no errors in any of the expressions or any of the explanations. Their explanations are perfectly all right. So for theory, I recommend a book called University Physics by Young and Friedman. All right, that has got wonderful theory. Okay, but again, the only problem is that the language of the book gets slightly technical. So University Physics is one book, or you can have, of course, Resnick and Halliday. So these are two books which are international books, have great repute internationally. Both these books are almost more than 50 years old, by the way. So obviously their theory is well accepted, well respected. So you cannot go wrong with your theory with either of these books. The only problem with these books is that the language can be slightly technical. Why? Because they have to mention everything in precise technical terms so that there is no distortion in the meaning. Okay. For questions, of course, H.C. Verma is the first. So this for theory. Now the only problem is, again, I would not recommend any of the Indian books for theory, because what they do is that in order to simplify the language, they make a lot of mistakes in translations. Okay. So for problems, the first one is H.C. Verma. That's a must book to solve. H.C. Verma is definitely the first book, and then you can solve all the all the sheets that your teachers would be giving you in your classes. And finally, if you are ready, maybe you can solve Erudov. This is a must. This is a must. Now, if you feel ready, then Erudov maybe. Even if you don't solve Erudov, that is perfectly all right. See, we guys used to solve Erudov because when I took JEE, JEE was subjective. So there you had lengthy problems, complex problems, and I think we were given at least 10 to 12 minutes to solve one problem. So there, the kind of problems that were asked, there it was important for us to solve Erudov. All right. For problematic, which book? Okay, so I don't understand what you're trying to say, Mahendra. Anyways, moving forward, plus all sheets that your teachers will give you in your courses. Sheets given, practice sheets that every teacher gives, given in courses. So that is also a must. And beyond that, you also have a lot of question banks. Okay, so previous year JEE problems, definitely must. Previous year JEE papers is a must. Again, a must solve. All right, rest is up to you. If you find more time, then you can find more books. All right. So yes, wrapping this session up, let me remind you how you can get your Unacademy subscriptions. If you have downloaded the app, go to the plus section, select your goal as IIT JEE and click on get subscription. Where did you take coaching? I took coaching from Lucknow, only from local teachers. That time, back then, we did not used to have these organized institutes very much. All right. I joined all my classes in Lucknow that time, individual teachers. So I used to go to one teacher for physics, to another teacher for chemistry, to a third teacher for maths. All right, that time that was the system. We used to have classes by individual teachers. All right. So those were in Lucknow. All of them were in Lucknow. Those were individual teachers. They were famous. Okay. So it is now that you have institutes like, FitJEE, Akash and all. Now Unacademy also is providing you online courses. So you can join any of them. I myself was teaching for the longest duration at FitJEE. I was teaching at FitJEE, by the way. Okay. For 4 years almost I taught at FitJEE. Then I have also taught at other. Intelligent sir in Unacademy? Okay, I don't know. I am one definitely. Alright. Moving forward with the Unacademy subscriptions, you will realize that the fees of these subscriptions is already very low. See, for 2 years it comes to 36,000, 1,500 a month. For 12 months, it comes to 30,000, which is 2,500 a month. Now, all your offline coachings, they charge almost 10 times this fees. On an average, they charge 10 times this fees. So, Unacademy is providing you very quality content, very close to offline teaching experience at these prices. I think the Unacademy subscription is a must-have. All right. Next, if you get this subscription using this code, which is my code. So, if you want to enroll in my courses on the Unacademy Plus app, you can get your subscriptions using this code RDLive. I will be starting my courses next month in September. All right. So join using this code, and you will also get an additional 10% off. See, this is what, 1,500 a month. 1,500 a month. If you use this code, it will come out to be 1,350 a month. It gives you a 10% off. So 1,350 a month is not at all costly. Next, and even if you can't afford that, then you can always follow me on YouTube. These sessions are completely free. Don't worry about it. Bye, Lata. So you can follow me here on JEE English channel. These sessions are completely free. Follow me here. These are completely free. All right. If you can afford it, then you should definitely go for the subscription. Otherwise, this is good. All right. Bye-bye. Next, if you like today's lecture, then press the like button and share it with your friends. So share this. This is free content being provided to you. Very good quality content being provided to you absolutely free by Unacademy. So share it with as many people as you can. Everybody should benefit from this. Don't forget to press the bell icon, and the PDF of all the slides that were used in today's lecture would be available for download by tomorrow or day after maximum. All right. Yes, Deepika, tell me. For those of you who are following us on the JEE English channel, you can join, you can connect with us on the Telegram app using the link shown above. Yes, Deepika, tell me. I am waiting. What? Teach in Vedantu. Okay. Why? Oh. Okay, no. Unacademy people have hired me. They approached me, so I am going to be teaching here only. Yes, I will upload that within 2 days. Within 2 days. By Sunday, I think you should have the PDF, available for download. Don't worry. Now, before I leave you guys, please remember, let me remind you again, my code is RDLive. Use this code to get your subscriptions and enjoy an additional 10% off on your subscription fees. So, all right, I'll see you guys next on Monday. Okay, till then, you guys take care and keep practicing your problems. All right. If you see the previous lecture, PDFs would be uploaded. I have uploaded it from my end. The Unacademy team would be making them available for download very, very soon. Yes, Hemlata, I am intelligent. I am in fact also a Mensa member, if you know what that is. I am also a Mensa International member. Okay, as I said, I don't tell you a lot about myself because that slide does not allow for me to tell you everything. So, Hemlata, yes, you can Google what Mensa International is. You can Google what Mensa International is. I am supposed to have an IQ of around 155. All right, anyhow. So, I will see you guys on Monday, and till then, you guys keep practicing, keep studying hard. So, take care. Bye-bye.